Greetings and welcome once again. So today I'm going to show you how to uh, use Geogebra to study the Holy Grail of Calculus. And then you can actually verify for yourself that it works for any particular function. And you also learn how to use Geogebra. So what I've done is, the only thing I've done here is that I've copied the identities here so that I don't have to waste time with them. And then I'm going to just go ahead and choose a function. Let's say, let's say 0.125 or 1/8 x squared, like that. Normally when I use functions, I like to have them as a blue color, and I like to have the opacity full and make the line about 7 long. Also, I set the labeling to no new objects and 5 decimal places. I don't like GeoGebra to label the objects for me. So I've got F here, and then I also want to draw f of x, like that. Nope, f of x. Yep. And I don't really want to show it right now, so I'm going to just hide it for the time being. Then I need to put in a few points. So I'm going to put a point here and a point here. Then I'm going to join these points because I want a secant, like that. And then I want a tangent line right over here. So I'll come up here and I'll choose tangents, like so. Okay, then I don't like to have that line going across a page. So I just put 2 points on it, like that. And I hide the object. And of course I join the tangent like that. Okay, so now I like to have the secant line the same color as this expression here, right? So what I'll do is I'll go to settings. Let's just make this a bit smaller. Choose the color red. Make the opacity 100, 7, and there we've got the non-parallel secant line. And because these are movable, I like to make them big and hollow and give them the color green to indicate that they can be moved. Okay, so it's just a custom of mine. You don't have to follow it, but it helps when I'm looking at applets that I haven't worked at for a long time. And of course, these little bits here, I simply like to give them this light blue color. They are movable, but I don't need to move them if I don't want to, okay, because it doesn't change anything. And finally, the tangent line has to have the color green, right? So I'm going to choose the color green. Or am I on the tangent line there? Let me just close this. Tangent line. I just want to make sure I'm on the tangent line. Okay, settings. So I want to choose the color green. Again, opacity 107, like that. And now what I want to do is I want to fill in the similar triangles. Okay, so what I'm going to need to do is I'm going to have a horizontal through this point and a vertical through this point. All right, so what I'll say here is this point here is actually A. So I'll say y is equal to y of A, like so. And then I want a vertical through this point here, which is B. So I'll say x is equal to x of B, like so. And then I want to intersect all these points. Now, I'll know if it's an intersection if the dot turns to black. If it doesn't turn black, it hasn't intersected. So that's a success. And this is a success too. And then, of course, I need one more horizontal line through this point here. Okay. So, and this point here will be point E. So what I will do is I will say y is equal to y of E, like so. And I'll put another point right over there, intersect the secant line with this horizontal line, like so. Oops, that didn't work because it's blue, right? So I'll just undo and try it again. Oh, and that worked. Now I don't want those long lines, so I'm going to basically hide them. You can't delete them because you need them, so you just hide them like that. And that's hidden, and that's hidden. And now we join up all the lines here, so we get segments. So we'll do this segment here, which is H, this one, which is F2, and this one, which is F1, and this one here, which is just a parallel to H. Okay, and now we can give these the right colors and the right labels. This is going to be H, like so. And we want the color magenta, and of course, the same as the other lines. This color here is going to be green, like so. And we want to label it F2. Okay. And then this color here is going to be the gold color, right? Which is that one there. And the style is same as the others. And we're going to label that F1, like so. Okay. And later on, say for example, if we want to see the values, we can just drop down here and say caption and value, and it prints out the value. Okay, so that would be the value, similar to all the others. Right now, I just want to keep it simple, so it's just caption. Now, I do not need these points, so I'm going to hide them. Okay, like so. Hide, and I don't need that point either. Just like to keep things simple. Hide this too. So now we can move this like this and this like this. And of course, if we did the same thing on this side, let's just get that out of the way, and did this, then we should have the same story over here, right? Okay, so we can see that the theorem will work the same way, but obviously I've forgotten to do something here. So you can get it to work on both sides. I'm not really going to bother about that. I'm just going to focus on one side, like so. Okay, so I got it back to where I had it. Now, so we can move this anywhere along here, and it's fine as long as it's on the right side of the y-axis. I haven't actually made provision for having a curve concave up like that towards the left, but it's easy to do, and the theorem works exactly the same. So now you can actually test this with any particular function. Okay, you can say geometrically that the tangent line is equal to f2 over h. Okay, because this expression here that you see on the top is the geometric version. Now, algebra is a weaker form, okay? This is the algebraic version. So it's not always easy to separate x and the terms in h. So for example, you might get an expression where you've got 2x and then you've got something like plus 1 over x plus h. You cannot just set h is equal to 0 here because you'll still have, well, actually you can here because you'll have 1 over x. But you have to be careful when this expression here doesn't evaluate properly. So for example, you need to make sure that the denominators in any part of this slope difference, are never 0. And of course, there are many ways to do this. It's exactly the same way as you do it in your mainstream calculus, where you separate the x terms from the h terms. And then, of course, it's perfectly acceptable to simply discard this expression, which is the same as discarding that, which is the same as setting h equals to 0. Okay, so you could literally throw away this term, and this term here, this expression, would give you the derivative. Now, in algebra, as I said, it may not always be easy to find it, but in geometry, this applies to every particular function. So you can, for example, choose, let's say the sine function. Let's go back up here and say, let's do this. Say, come on, let's say sine of x. So, and bring that up the right way. And of course, it will work if you are able to, like, see, for example, here, it's on the same side, so it's not a problem. But you have to tell the applet that it needs to create the intersection points and everything else in the right order. But this will always give you the derivative and the slope difference, okay? Because in this formula, this expression on the left here, this red expression, is the slope of the non-parallel secant line. This expression is the slope of the tangent line. And this expression is the difference between the tangent line slope and the non-parallel secant line slope. So then the other thing that you need to know is that you can actually also find the integral by positioning these correctly. So let's see, where is this? Let's put this there. So say, for example, you wanted to find the integral of this derivative. Okay, so the derivative would be the red line. So you'd want to find the area here. Okay, so in other words, if we get a pen, if you wanted to find this area, like so, all this area, then it would simply be this expression here multiplied by h. That's all it would be, all right? Or this expression multiplied by h. So, so you get both the derivative and the definite integral, and it works for every single smooth function. There is no exception, okay? This is why it's called the Holy Grail of Calculus. And of course, I'll put a link to an applet that already works, and that you don't have to see all this because I've done this in a hurry. But I do have another applet that works a lot better, and I'll put a link to it in the details section. And that's pretty much it. I hope you've learned something about GeoGebra and something about the Historic Geometric Theorem and the Holy Grail, because the Holy Grail allows you to define the derivative and the definite integral, okay? And this is the definite integral, which in mainstream calculus is this, all right? So if you're not already a subscriber, become one, tell your friends about this, click like, and also become a follower on Academia, right? So I'll place a link to Academia. This is my Academia site here. I'll place a link to my profile, and you can view all my articles and videos and anything else. And of course, I'll place a link to a GoFundMe page if you want to donate. Would be really nice if you were able to spare a few dollars. If not, that's okay too. My name is John Gabriel. This is a new calculus channel. Till next time, goodbye.